Alright, this is Chapter 4 homework for Physics 201. 6 kilogram object undergoes an acceleration of 2 meters per second squared. What is the magnitude of the resultant force acting upon it? So this simple application, F equals ma. That's equal to 6 kilograms times 2 meters per second squared. It's equal to 12 newtons. The same force is applied to a 4 kilogram object. What acceleration is produced? Again, Newton's second law. The sum of the forces equals the mass times the acceleration. There's only one force here. That's 12 newtons. That's equal to 4 kilograms times the acceleration. So the acceleration is equal to 3 meters per second squared. Pretty basic problem. Might see something like that on the quiz, but probably not on the test. A freight train has a mass of 1.5 times 10 to the 7 kilograms. The locomotive can exert a constant pull of 7.5 times 10 to the 5th. How long does it take to increase the speed of the train from rest to 80 kilometers per hour? Let's just write down everything that we know first. The mass is 15 million kilograms, or 1.5 times 10 to the 7 kilograms. The force that your locomotive can exert is 7.5 times 10 to the 5th newtons. V naught, the initial speed, is 0. And then V final is 80 kilometers per hour. I want to go ahead and convert that into meters per second. 1 kilometer, there are 1,000 meters. 3,600 seconds in an hour. That gives me 22 meters per second, but keeping proper sig figs is 20 meters per second. Alright, so now I want to know how long does it take to increase the speed from rest to that final velocity? Well, from our equations for kinematics, we know that V is equal to V naught plus AT. Here, I don't know time, which I want to know. I also don't know acceleration. Alright, however, I know that F equals ma, so I can say that A equals F over m. I can take that and plug it in for the acceleration, and so I get V is equal to V naught, which is 0, times F over m times t. And then if I solve that for t, that is Vm over F. V is 20 meters per second. M is 1.5 times 10 to the 7th kilograms. And F is 7.5 times 10 to the 5th. That's in, is that F? That's newtons. Let's see, that gives me I get 400 seconds. Next one, number 3, boat moves through water with two forces acting on it. One is a 2,000 Newton force pushed by the water on the propeller, and the other is 1,800 Newton resistive force due to the water around the bow. What is the acceleration of the 1,000 kilogram boat? If it starts from rest, how far will it move in 10 seconds, and what will its velocity be at the end of that time? So here we have an object with two forces acting on it, my boat. I have a force that's pushing it forward. I'm going to call that, well, I'll just say that's 2,000 newtons. And then I have a resistive force. It's going to be 1,800 newtons. All right. I know that the mass is 1,000 kilograms. We'll call this the NSU boat. All right, 1,000 kilograms. And I want to know its acceleration. How far does it go in 10 seconds, and what is its final speed? Well, the acceleration is pretty easy for A. The net force equals ma. The net force here is the sum of the two forces, the vector sum. It's going to be 2,000 minus 1,800 newtons. That's equal to 1,000 kilograms times the acceleration. So the acceleration is 200 over 1,000. So that's newtons over kilograms. A newton is a kilogram meter per second squared, so that gives me meters per second squared, which is 0.2 meters per second squared. That's part A. Then part B, how far does it go? Well, I know that x equals v naught t plus 1/2 at squared. V naught, is it start at rest? Yeah, if it starts from rest, so this is 0. So that's equal to 1/2 times 0.2 times 10 seconds squared. That gives me 10 meters. And then finally in part C, what is its velocity? This is all still sort of basic kinematics. V naught again is 0, A is 0.2 times the time. Oh, by the way, this should have been parentheses. 0.2 times 10 is 2 meters per second. It's a slightly more complicated problem. Probably not exactly what you'll see on the midterm, but getting a little more difficult. Okay, number 4. You have 2 blocks fastened to the ceiling of an elevator, as in this figure. The mass of each is 5 kilograms. The elevator accelerates upward at 2 meters per second squared. Find the tension in each rope. It's useful to take each block separately and label all the forces on them. So I'm going to label the forces on this top block. We'll call this FT1. That's the tension in the top rope. FW1. That's the weight of the block. And then you also have FT2. That's the tension from the second rope that's pulling down on that block. In the bottom block, you have this tension. This is also FT2. And then you have the weight of the second block. So I'll call this M1 up here, and I'll call this M2. All right, so I will take the bottom block first. It's just a little simpler. Take the bottom block first. The reason I'm doing this is because if I take the bottom block here, all right, I'm going to find what is FT2, and then I can use FT2 because I know that FT2, the tension in that bottom rope, affects the tension in the top rope. All right. If that's not obvious to you now, as you practice, it should become more obvious. So let's do this block first. All right. You redraw this just as a lone block. This is mass 2. It has 2 forces acting on it, FT2, FW2. And it's accelerating upward. I say the sum of the forces equals the mass times the acceleration. The sum of the forces is FT2 minus FW2, and that's equal to MA. The bottom and the top block both accelerate at the same rate. Right? So the acceleration is the same. Now I'm looking for FT2. FT2 equals MA plus FW2. That's equal to 5 kilograms. Actually, let me write that out. M2A plus M2G. That's equal to 5 kilograms times A plus G. That's 2 plus 9.8. Which is equal to 59 newtons. All right, so that's one of my forces, the tensions in the rope. Now let's take the top block, which has more forces acting on it. It has FT1, FW1, that's the weight of that block. And then it also has the tension in the second rope, FT2. This is M1. Now I do the sum of the forces equals M times A. FT1 minus FW1 minus FT2 equals M1A. Now here the 2 blocks have the same mass. All right, so this doesn't matter if you get your masses mixed up. But if they had different masses, you have to be very careful to make sure that you get your M1 and your M2 straight. All right, so that you get the appropriate number. If I'm talking about block 1, I always use M1. If I'm talking about block 2, I always use M2. All right, so I'm looking for FT2, so I'm just going to solve this for FT2 is equal to FT1 minus FW1 minus M1A. All right, so I know FT1, it's 50, or excuse me, I'm looking for FT1. Sorry, I made a mistake there. Let me go back. You can probably just change some signs here. But I'm looking for FT1, which is equal to FW1 plus FT2 plus M1A. All right, so that's M1 times 9.8 plus 59 newtons. That's from down here. Plus M1 times 2 meters per second squared. That's from the problem. And if I put in M1 as 5 kilograms, I get 120 newtons. 120 newtons, that's right. All right. Problem number 4. That would be appropriate for an exam, though there are some more complicated ones, such as this one. Have a block in this figure has a mass of 5 kilograms. The inclined plane has an angle of 30 degrees. That's this angle. Whenever we're talking about an inclined plane, that's the angle we'll use to define it. Coefficient of static friction is 0.2. I'm just going to start writing some of these things down. The mass of the block is 5 kilograms. The coefficient of static friction, that's mu s, is equal to 0.1. The coefficient of kinetic friction is 0. Excuse me, get those switched up. Static friction is 0.2. Kinetic is 0.1. Remember, the coefficient of kinetic friction is almost always, basically always, less than the coefficient of static friction. I now want to know what is F up in order for the block to remain in place. So in my first situation, the velocity of the block is going to equal 0, and the acceleration of the block will equal 0. All right, in order for it to stay in place. Let's label our forces here. I have several forces at work. I have the normal force. I have the weight of the block. And then I also have the static frictional force. And now you must ask yourself the question, what is the direction of the static frictional force? This object wants to move downward. All right. And so my static frictional force is going to oppose the direction of that motion. So my static frictional force is up. I can draw in my axes. With an inclined plane, it's always best to do your axes along these planes of the incline. And that makes this angle right here be 60 degrees. All right, if you blow up that section, let me just sketch this out. If I have something dropping down here, you see this angle is 30. That means that this angle has to be 60, and this angle is the same as this angle, 60 degrees. That's pretty standard when you're dealing with an inclined plane to work with the angles in that way, and we'll follow that convention in this class. All right. So what does F up need to be in order for the block to remain stationary? Let's draw a vector diagram. As I do that, I'm going to go ahead. Actually, no, I'll go ahead and write out all the vectors. So I have F in, F up, and Fs. And then I have Fw over here, but it's not on the X or Y axis. It's at 60 degrees. And now I also want to resolve any vectors that aren't on the axis. F in, F up, Fs. This vector is my y component of the weight, FW sine of 60, and this is going to be FW cosine of 60. Now, I can apply the Newton's second law. Sum of the forces equals ma, but I'm going to do it both in the x and the y direction. So I always like to just write out the equations, right? So I say sum of the forces in the x direction equals mass times acceleration. But in this case, I know that my acceleration is equal to 0, so it's just equal to 0. And then I can also say the sum of the forces in the y direction is equal to 0. So let's do the x direction first. I have FW cosine 60 minus F up minus Fs equals 0. And then the sum of the forces in the y direction is Fn minus Fw sine 60. All right, now that's equal to 0. So you basically do this up to this point for every inclined plane problem. Write out your x and y equations for the forces in the x and y directions. And then you want to ask yourself, well, what is it that I'm looking for? And I don't know, what is it I'm looking for? I'm looking for F up. All right, so I have F up right here, but I don't know what Fs is. All right, so I need to figure out what Fs is in some way so I can solve this equation on the left-hand side for F up. Now, I know that Fs, in this case, since it's a minimum, is equal to mu s times the normal force. But I don't know yet what the normal force is. However, I can say from the equation here that Fn equals Fw sine of 60. All right, and if I solve that for my normal force, I get 5 times 9.8 times sine of 60. The normal force is equal to 40 newtons. All right, and then I solve for Fs is equal to mu s times the normal force. That's equal to 0.2 times 40 newtons. And I get an Fs of 8 newtons. All right, so now I know everything in this left-hand equation except for F up. F up. So I'm going to solve it for F up. I have F up equals Fw cosine 60 minus Fs, which I now know. So that's going to be the mass, which is 5 kilograms. 5 times 9.8. That's 49. Oh, excuse me, times cosine of 60 minus 8 newtons. So I get 16.5, 17 newtons. And that's the answer, 17 newtons. That's what the force, minimum force required in order to make the block stay in place. Now the second part of this problem asks, what is the force required? Our F up is equal to 55 newtons. What is the acceleration of the block? And now this problem is quite a bit different. It's going to be a little more complicated. But my first question I want to ask myself is, what is the direction of the frictional force? Now the direction of the frictional force always opposes the direction of motion. So you ask yourself the question, well, if F up is 55 newtons, what is the direction of the motion? All right. Since I know that I need 17 newtons to just hold the block in place, if I have a force that's greater than that, it's going to move up the inclined plane. If I have a force that's less than 17 newtons, like for example, if I said that F up was equal to 5 newtons, then the block would move down the inclined plane. So it's going to change a bit. I'm going to erase some of this because it's all going to change. I'll erase all this. You should have a second page in your book. If I'm not mistaken, I put in 2 pages. Both of these are sort of one-page problems. Take this away. I'll take this away. All right, everything else should stay the same, but now my only difference is that now I'm going to have Fk pointing in this direction. Fk is going to be in that direction because it opposes the direction of motion, and for this second part, my block is going to be accelerating up the inclined plane. And I want to know what is the acceleration of that block. All right, I'm going to make this change here. So I have Fk here. And then I'm just going to go and write out the sum of the forces in the x and y directions instead of writing out the new resolved vector diagram. All right, give me just a second. All right, so the sum of the forces in the x direction equals mass times acceleration. And now my acceleration isn't 0, so it makes the problem a bit more difficult. So if I add up these forces, I get F up, pardon me, Fk plus Fw cosine 60 minus F up equals mass times acceleration. All right, and then the sum of the forces in the y direction, that's equal to ma(y). This is ma(x). Now, the acceleration in the y direction is equal to 0. So this is going to be just like what I had before. Fn minus Fw sine of 60, that's equal to 0. Okay, so now I have a couple different unknowns. I don't know what Fk is, and I don't know what the acceleration is. All right, but just like I did before, I can figure out what is my normal force. And it's the same as what it was before. It's just Fw sine 60. Fw sine 60, which is 40 newtons. And then I can solve for Fk, which is equal to mu k times the normal force. And my mu k is 0.1 times 40, so that's equal to 4 newtons. All right, so that's my Fk. And I can use that over here. I'm going to solve this for A, and I'll go ahead and put in some numbers as well. 4 newtons plus Fw, which is going to be 5 times 9.8 times cosine 60. That's also in newtons. Minus F up, which is 55 newtons. And then that's all going to be divided by the mass of the block, which is 5 kilograms. So I get 4 I get minus 5.3 meters per second squared. So I want to ask yourself the question, why does it come out negative? Because we've always said that our acceleration in this case is going to be in that direction, and we take left to be negative. All right, so the acceleration is minus 5.3 meters per second squared in the negative x direction. All right, this figure shows a block suspended by 2 ropes. The ropes are attached to the ceiling at angles as shown. If the mass of the block is 10 kilograms, what is the tension in the rope on the left? All right, so I want to list my forces here. List my forces, and then I will find the tension on each rope. All right, I have the weight of the block, FW. I have the tension in the left. I'm going to call this FTL for tension and on the left. And then I have the tension on the right, and I'll call this FTR. All right, now I can just look at it and tell you that the tension in the left is going to be bigger than the tension on the right. All right, but let's see, in particular, I'm looking for the tension in the left, but I could potentially ask you for either. All right, so I need to get my angles correct here. This angle is 60 degrees, and this angle is 30 degrees. If that's unclear to me, you should come see me, and we'll sort of do a primer on geometry. All right, I want to draw my vector diagram. Eventually, you might get sort of out of this where you don't need to draw all these vector diagrams, but I think just to start, it's useful. Right, so I have FW. It's useful just to sort of keep everything straight. I'll just call this FR. This is at 30 degrees. And then I have FL at 60 degrees. All right, now I'm going to resolve my vectors. It's FW, FR cosine 30. Let me write that down below. Don't get too messy. This is FR cosine 30. This is going to be FR sine of 30. This is going to be FL cosine of 60. And then this is going to be FL sine of 60. So those are my resolved vectors. And then I can do the sum of the forces in the y direction and in the x direction. Sum of the forces in the y equals FL sine 60 plus FR sine 30 minus FW. And this is a statics problem. That means the acceleration equals 0. So that mass times the acceleration term is equal to 0. And then I'm going to write out the sum of the forces in the x direction. FR cosine 30 minus FL cosine 60. That's equal to 0. All right, now I'm looking for FL. Both of these equations have two unknowns. The two unknowns are FR and FL, but I'm looking for FL. So I'm going to solve, let's see, I'll solve this bottom equation for FR. So I'm going to solve this equation for FR, and I find that FR is equal to FL cosine 60 divided by cosine of 30. That means that FR is 0.58 times FL. Okay? So I'm going to take this expression for FR, I'm going to plug it in here. It's a system of equations. And then I can come back and solve this for FL. So I get FL sine 60 plus 0.58 FL sine of 30 minus my mass, which is 10 kilograms, times 9.8. That's equal to 0. And then I solve this for FL, and I'll let you do that algebra on your own, but I get an FL of 82 newtons, or 80 newtons. 82 is equal to 80 newtons. Keeping proper sig figs. It's number 6. Dock worker loading crates on a ship finds that a 20 kilogram crate initially at rest on a horizontal surface requires 75 newton horizontal force to set it in motion. However, after the crate is in motion, a horizontal force of 60 newtons is required to keep it moving with a constant speed. Find the coefficients of static and kinetic friction. All right, first, I know that my static friction is equal to mu s times the normal force, and my kinetic friction is mu k times the normal force. So I need to know two things. First of all, I need to know the normal force for each. And you know, for a block sitting on a horizontal surface, the normal force, if it's not moving, is equal to the weight. All right, so I can say Fn minus Fw equals 0, so Fn equals Fw, which in this case is m times g, that's 20 kilograms, times 9.8, which is gives me a normal force of 200 newtons. All right, so now I know my normal force, but now I have two forces here that are given, 75 newtons and 60 newtons. I need to know which of those is the static frictional force and which is the kinetic frictional force. The static frictional force is the force required to get something moving. That is the maximum force required to push on something to get it moving. So Fs is equal to 75 newtons. We talked about this in class. Fk then is 60 newtons. All right, so now I just solve each of these for mu s and mu k. Mu s is equal to Fs over Fn. That is 75 over 200. Notice the units cancel out. There are no units for coefficient of static friction or kinetic friction. That's equal to 0.4. And then mu k is 60 over 200. I get 0.3. So those are my static and kinetic frictional forces. 1.25 kilogram object is moving in the x direction at 17.4 meters per second. 3.41 seconds later, it's moving 26.8 meters per second at 34 degrees to the x-axis. What are the magnitude and direction of the force applied during this time, and what is the force in vector notation? Let's just write down what we know. This is similar to what we've done, but now it's extended into more than one dimension. So my mass is 1.25 kilograms. I'm going to write it over here to the side. It's moving in the x direction initially, so this is my v naught at 17.4 meters per second. I'm going to go ahead and give a vector notation, so that's in the I direction. 3.41 seconds later, it's moving by v final at 26.8 meters per second. At 34 degrees to the x-axis. All right, what are the magnitude and direction of the force applied during this time? In order to find the force, I need to know its acceleration. All right. In order to find the acceleration, given this information, I can return back to my kinematics equation like this and find the acceleration. All right, but first, my first order is to take that final velocity and put it in vector notation. So Vf is going to equal Vfx in the I direction plus Vfy in the j direction. That's going to be Vf cosine of theta, cosine of 34 in this case, the I direction, plus Vf, I'll go and write in the number, 26.8 cosine of 34. Just make sure you're not confused. I'm going to go ahead and write in Vf here. This is 26.8. Oh, I'm sorry. This should be sine for the y component. All right, so that'll give me my final velocity in vector notation, and that works out to be 22.2 I plus 15.0 J. That's in meters per second. All right, so that's my Vf. Now, I can find my acceleration from this equation. My acceleration equals Vf minus V naught over t. And just like we did in the previous chapter, when I'm dealing with these vectors and vector notation, I just group the like components together. I group the x components together, and I group the y components together. So it looks like this. I get 22.2 I plus 15j. and my initial was 17.4, minus 17.4 in the I direction, and that's all over my time, which is 3.41 seconds. And these were in meters per second up here. All right, so I combine these two terms, and this works out to be 22 minus 17.4. That's 4.80 in the I, plus 15.0 J, divided by 3.41 seconds. And that gives me an acceleration of 1.41 I minus 0.704 J. That's in meters per second squared. Okay, so now I really want to know what is the force in vector notation. I have the acceleration, so this is pretty easy. Just the mass times that vector. That's going to be 1.25 kilograms times 1.41 I minus 0.704 J. And so that works out to be 1.76 I minus 0.880 J, and that's in newtons. All right, so that's my force in vector notation. Now I also want to know the force, the magnitude and direction of that force. The magnitude of the force, just use the Pythagorean theorem, 1.76 squared plus 0.880 squared. I get 1.97. And the angle theta is the inverse tangent of the y over the x components. That's 0.880 over 1.76. Remember, this comes about. That's the y component. That's the x component. That gives me my angle theta, which is 26.6 degrees. As I said, that's not the answer. I also need to know what is the direction of that. I always like to plot out my vectors. Looking at these two components, I have a positive x component and a negative y component. That means that my final vector is going to be at an angle below the positive x-axis. All right, so below the positive x-axis. So that's part of the answer. This is the magnitude and direction. That's number 8. Okay. A 2 kilogram and a 3 kilogram mass are on a horizontal frictionless surface connected by a massless spring with a spring constant of 140 newtons per meter. 30 Newton force is applied to the larger mass, as shown in this figure. How much does the spring stretch from its equilibrium length? The force required to compress or stretch the spring is given by Hooke's law. It's F equals kx, where F is the force and x is the displacement of the spring. So you have a couple of forces that are acting on this. Several forces, actually. Just sort of sketch them out first of all. I'm going to call this mass M1, and I'll call this one M2, just so we can keep them straight. This is going to be FW1, FW2. Though, let's see, we don't need that information right now, but we'll need it a little later for the next problem. So I'll go ahead and write it out. And that's not FW1, I'm sorry, that's FN1. So the weight of the first block, and then the normal force. This is FN2. And this is FW2. We also have the forces that are acting on the spring, or the forces exerted by the spring. Those go in this direction, and they're both the same, equal and opposite, and they're Fs. All right. Each block is attached to the same spring, and it feels the same force provided by that spring. All right, that string, when you start pulling on it with this force F to the right, which we're told is 30 newtons, that string stretches out, all right, and we want to know how much does it stretch. Let's just do our sum of the forces. As I said, even though I've drawn the y forces here, I'm not going to use those, but I'll use those in the next problem. So I always like to draw all of my forces as a matter of practice, all right, so that you sort of do the same thing every time you encounter a vector force problem like this, a force vector problem. All right, but we're just going to be concerned with the forces in the x direction. So let's do the sum of the forces in the x equals to the mass times the acceleration. Let's do it for m1. We only have one force on the left block, and that is Fs, and that's going to equal m1 times A. All right. For m2, we have F minus Fs equals m2A. Okay, so further, I can also, for both of these equations, put in Hooke's law, which I was told up here. That's Hooke's law. That is that Fs is going to equal Kx. So I'm just going to put in both of those for both of these equations. F minus Kx equals m2a. And then, so now I've written my equations. Now I want to ask myself, well, what is it I'm looking for? I'm looking for x, right? I'm looking for the how much does the string stretch from its equilibrium length. What is x? What don't I know? Let's see, I know k, I know m1, but I don't know the acceleration. So I have two unknowns, x and the acceleration, the elongation and the acceleration. So I'm going to just solve this system of equations. I'm going to solve this one over here for a. A is equal to kx over m1. And then I'm going to take this, and I'll plug it in over here for a. So then on this right equation, I'll only have one unknown. F minus kx is equal to m2 times kx over m1. So I'll solve that for x. See if I combine all my x terms, I get f equals 1 plus m2 over m1 times kx. And then I solve that for x is equal to f over 1 plus m2 over m1 times k. And that gives me an x equal to 30 over 1 plus 3 halves times 140 newtons per meter of 0.086 meters. All right, which is 8.6 centimeters. If you're a stickler about your sig figs, you'll notice that I've used an inappropriate number of sig figs. But I just want to keep 2 sig figs here because in the next problem we get a very similar number. I just want to show that they're different. So just bear with me. I'm not going to write 9 centimeters. I'm just going to keep it at 8.6 centimeters. All right, that's a good problem. I mean, you should be able to do something similar to that, something with 2 blocks, all right, 2 bodies, where you have to include things, different types of forces, spring forces in this case, or like in the next problem where you have to include frictional forces. I think this is the last one. Yeah, so in this one, it's just like the previous problem, but now the coefficient of kinetic friction is going to be 0.2. I'm going to make a change here to make it 0.2. I've changed this on the online, but it's still 0.1 in your book, so you need to make that change in your book. All right, so what is the elongation of the spring if the kinetic frictional force between the floor and each of the blocks is 0.2? Okay, so I have all the same. I'm going to sketch out my 2 blocks and just label all the forces. This is M1, and I have forces, the normal force, Fn1 and Fw1. I have the spring, Fs, and then I also have the kinetic frictional force, Fk1, which I didn't have before. So that's one block. And then this is my M2 block, the second block, the one on the right. I have my normal force, Fn2, Fw2. I have the force that's pulling to the right, which is going to be the same as the other force, 30 newtons. And then I have Fs, that's the force of the spring, just like in the previous one. But now I also have Fk, and this is Fk2. All right, so I have the two blocks, and I've added in, the one force I've added in is the kinetic frictional force. Okay, so first thing I want to do is figure out what is the kinetic frictional force. All right, and I can do that because I know the coefficient of kinetic friction, and I can pretty easily find the normal force. So just like we did before, I'm going to first find the normal force, and then I'll find the kinetic frictional force. So I'm going to do that by looking at the sum of the forces in the y direction first. So I'm just going to say for the block on the left, that's Fn1 minus Fw1 is equal to may, but the acceleration in the y direction is 0. All right, and I'll do this in parallel on the second side. Fn2 minus Fw2 is equal to may, which is equal to 0. All right, so Fn1 is equal then to Fw1. That's going to be m1, which is 2 kilograms times 9.8, which is 20 newtons. In a similar way, I can find Fn2 is going to be 3 kilograms times 9.8, which is 29 newtons. Now, I can find the Fk1. That's going to equal mu k Fn1, which is 0.2 times 20, which is 4 newtons. And then Fk2 is equal to 0.2 times 29, which is 6 newtons. All right, so now I'm fairly well equipped to continue on. Let's do that first. And now let's look at the sum of the forces in the x direction. Sum of the forces in the x direction is going to be, for the left, Fs minus Fk1 is equal to m1 times the acceleration of the blocks. And actually, I'm going to go ahead and replace this Fs with Kx. So Kx minus Fk1 equals m1a1. And then similarly over here, for the right block, I have F minus Fs minus Fk2. F minus Fs, which is just Kx, minus Fk2 is equal to m2 times the acceleration. So I'm looking for, I'm looking for x again. So I want to solve this right-hand side for the acceleration because I don't know the acceleration. That's an unknown. So a is equal to kx minus fk1 divided by m. I take that and I plug it in here, and then I just solve for x. All right, so I get f minus kx minus fk2 equals m2 times kx minus fk1 divided by m, that should be m1. All right, now you can put numbers in. The algebra gets a little complicated. I'm not going to recreate it here. But if I solve for x, just go ahead and put all your numbers in. You know f, it's 30. I know k, it's 140. I know fk2, I found it, it's 6. I know m2, I know m1, I know k again, I know fk1. Just put in all those numbers, and the only thing that you have left is x. And then if you solve for x, you find that x is equal to 0.094 meters. So you see with that addition of even just a little bit of kinetic frictional force, it causes the spring to elongate by a greater amount. Not by very much, but by a greater amount nonetheless. That's the end of Chapter 4 homework.